Hello there, my name is Maximus, back here with O-level physics, and we are still continuing with our waves topic. I hope everyone is doing well, and I hope you are enjoying these videos and you're making the very best use of them. You know, I put in a lot of time to create these videos just for you. Imagine. Yeah, I also appreciate the people that know how to appreciate. The people that are donating to these numbers, they are registered on mobile money. It's always not good to receive free things freely. At least it's good to appreciate. Yeah, if you donate to this noble cause of helping us learn from home, God will bless you. God will bless you. We still have very many things that we need to cover, but as for now, we are still operating under limited resources. I would have had even other teachers making their videos, and definitely they would need some pay. I only handle physics and math, and for mathematics I really need some good screen where I can do some screen recording, screen that is screen touch. But for now, we shall use the resources that are available. Nevertheless, I want to appreciate everyone that is committed to making sure that this project continues, and may God bless you. Okay, now this time we are looking at refraction of waves. Refraction of waves. Now, refraction of waves refers to the change in direction of waves as they move from one medium to another of different density. Now, when I talk about refraction of light, for light, you must include, you don't say different density, but different optical density. For now, we are looking at waves generally. So you say, a refraction refers to the change in the direction of waves as they move from one medium to another of different density. Now, when waves are refracted, the speed and wavelength change, but the frequency remains unchanged. I want you to note this, note it properly, that refraction does not affect frequency of the waves. It only affects the speed and the wavelength. And the speed is affected because the wavelength changes. Okay. So to understand how waves are refracted, let us consider the refraction of rays. So we shall look at, for those of you that have already covered light, you can easily relate this. If you haven't, don't worry. We shall consider refraction of for example, light rays. But let's look at rays generally. So a ray moving from a less dense medium, to a denser medium. This ought to be denser. To a denser medium, bends towards the normal. A ray moving from a less dense medium to a denser medium. Please put here an arrow, okay? Yeah, to a denser medium, bends towards the normal. And a ray moving from a denser medium to a less dense medium bends away from the normal. So what you have to understand is that the bending away from the normal is actually an indication of increase in the speed. And the bending towards the normal is an implication, it's an indication of a reduction or a decrease in speed. So a denser medium is like traveling where there is jam. You can move very fast. And a less dense medium is like traveling where there is less jam and you have a car. You know, you can just step on the gas, on the accelerator, and you zoom, move very fast. Okay, so we are saying that a ray moving from a less dense medium to a denser medium bends towards the normal. Note that. And the one moving from a denser medium to a less dense medium bends away from the normal. Now consider the following illustrations to understand this. Here we have a less dense medium. I've represented it with some like the sky. Yes, a less dense medium and then a denser medium. Now if a ray strikes the boundary, this point here where the ray strikes the boundary is called the point of incidence. The point of incidence in refraction. So we have a boundary here. So this is the point of incidence. At the point of incidence, if we draw a normal, the normal at the point of incidence. A normal means a perpendicular line. So if you look at the boundary, it's horizontal, and at the point of incidence, we've drawn a normal vertically. So the angle between the normal and the incident ray is always called I, the angle of incidence. Now look at what happens. Because the ray is moving from a less dense medium to a denser medium, what did we say happens? Does it bend towards the normal or away from the normal? Oh, yes, it bends towards the normal. It bends towards the normal. So instead of proceeding in this way, this was the original direction. You see, it has bent. It has bent. It has bent. It has bent, and it created an angle here, which we're calling the angle of refraction. The angle between the normal and the refracted ray is what we call the angle of refraction. If someone asks you, define the angle of refraction, honestly speaking, you shouldn't say they never taught us. It's very easy. The angle between the normal at the point of incidence and the refracted ray. Okay. So having understood that, let's also consider the other case where the ray is moving from a denser medium to a less dense medium. So still our ray striking the boundary between the two media. The plural of medium is media, M-E-D-I-A, media. So at this point of incidence, we still draw our normal. Now look at what happens. The angle of incidence still is indicated here, the angle between the normal and the incident ray. Now this time, instead of bending towards the normal, it bends away from the normal. The bigger the angle, this big angle indicates an increase in the speed. So the angle of refraction is big. It's bigger than before, because here the ray has bent away from the normal. So instead of continuing with the original direction, it bends away from the normal. This was the original direction indicated by the broken line. Now to demonstrate refraction of water waves in a repo tank, we create two regions of different depth. So if you have a repo tank and you want to demonstrate refraction of water waves, you have to create regions of different depth. There should be a shallow end and a deeper end. So the deeper end is the less dense medium, and the shallow end is the denser medium. Now the shallow region or the shallow end, to create it, all we need is just to place a glass plate in a repo tank. Okay, as long as you can place something so that the level of the water is shallower. Yeah, I think I should say the level of the water is low level. English. So we are saying the shallow region is created by placing a glass plate in a repo tank. The region where the glass plate is placed, that's the region where the water will be shallow, as you will see, as I will be illustrating more. Now let's look at the first case. Consider the refraction of waves moving from deep water to shallow water. Remember, the deep water is the less dense medium. You remember that? The deep water is the less dense medium, and the shallow water is the denser medium. The rays thus bend towards the normal, because now the rays will be moving from the less dense medium to the denser medium, and therefore the rays will have to bend towards the normal. We can just consider one ray only. And the speed and the wavelength of the wave will decrease. You know, deep water. If there is a wave, for those of you that have been at the beach before, if you have been at the beach before, you must have watched this, that when a wave is in the middle of the lake, for example, if you're at the Lake Victoria beaches, the waves appear big, but by the time they reach the shores where you are, they are very small. They can't even toss you. But in the middle of the lake, they can toss big boats and ships. So you realize that when water waves move from deep water to shallow water, the speed and the wavelength of those waves will decrease. Yeah, it will. But the frequency doesn't change. It remains the same. Put a full stop, eh? Right here, I put a full stop. Very good. Okay, now let's consider our diagrams. So here I have a boundary. There is a boundary between deep water, the upper region, and shallow water, this way. Now we said deep water is the less dense medium and shallow water is the denser medium. So those are plane wavefronts incident onto the boundary between deep water and shallow water. What will happen? How will they be refracted? I think I better just stop here so that you can finish. It's better that way. You can finish this thing. It's very easy. Someone is saying no, sir. All right, it's very easy. Let's finish it. So what we do is, if you want to know how to finish this diagram, always consider the rays. Now remember, if you have plane wavefronts, the ray is going to be drawn perpendicular to the wavefronts. So let's draw a ray. There is a ray here, perpendicular to the wavefronts, striking this point here. So this is what we call a point of incidence. Now, always, if you draw a normal there, what did we say happens? If a ray is moving from a less dense medium to a denser medium, what will happen? Does it bend away from the normal or towards the normal? It bends towards the normal. I knew you would get it right. So it bends towards the normal. It bends towards the normal. Someone just thought about it. They never said it. No problem. Definitely, even if you had said it, I couldn't hear you. So it bends towards the normal. Now, watch what I'm going to do. These wavefronts are perpendicular to this ray. The incident wavefronts here, they are perpendicular to the incident ray. That means even the refracted wavefronts have to be drawn perpendicular to the refracted ray. So what we do is, starting from the point of incidence, draw a line perpendicular to the refracted ray to represent the first wavefront, like that. I have drawn this line from this point of incidence and it's perpendicular to the refracted ray. For those of you that, if you want to measure, you can measure. I measure these things. You can stop there, you pause, you get a protractor and you measure the angle between this line and this one is 90 degrees. Okay, now from this very point here, we're going to draw another line perpendicular. Even from this point, we draw another one perpendicular, like that. Another one like that. Oh, yes. One like this, one like this. Then the rest we can just finish. You can finish that. Now, what do you observe? Look at the incident wavefronts, how they were spaced. Look at the refracted wavefronts. In the deep water, which is the less dense medium, they were more spaced. In the shallow water, which is the denser medium, they are closer to each other. Do you observe that? Or is only me seeing it? Yeah. It is true. Here, they are closer to each other in the shallow water. Now, here, if this is lambda 1, the first wavelength in the less dense medium, which is the deep water, and then this is lambda 2 in the shallow water, which is the denser medium. I'm going to take a case where I first take away the rays. Look at this. Let me take away the rays and show you what has happened. That is what has happened. These waves came like this and then they bent and were refracted like this. But I always advise you, when you're drawing, you draw like this so that you don't confuse yourself. Okay? Yeah, you're good children. Very good. Now, that's what we said has happened. I've explained everything. So let's look at the cross-sectional view. This side we have the deep water, which is the less dense medium. And then here we have the shallow water. I told you, just put a glass plate here to create this region. This is shallower than here. So look at the wavefronts here. Sorry, look at the wavelength. Because this crest, every crest represents the position of a wavefront. There's a wavefront here, there's another wavefront here, and another wavefront here. Now look at the distance between two successive crests here, lambda 1. Do you see that it's bigger than the wavelength in the shallow water? Do you see that? In the shallow water, the distance between two successive crests is smaller than the distance between two successive crests in the deep water. So that's the cross-sectional view. You can always pause these videos. That's why we use these videos. You pause. If you want to draw the diagram, you draw. No problem. Now, the speed v of the ripples or the water waves in deep water is given by, from the wave equation, v is equal to lambda f. So the speed of the water waves in the deep water will be v1 is equal to the lambda 1 times f. And at the same time, the speed v2 of the ripples in the shallow water, is given by v2 is equal to lambda 2f. Remember, f is constant. If you remember, refractive index n for the ray or for waves moving from medium 1 to medium 2 will be the velocity of that wave in medium 1 divided by the velocity of the wave in medium 2, which is v1 over v2. But v1 was lambda 1f, and v2 was lambda 2f. When you divide, the f and the f will fall, they will die, eh? So they have already kufadi. So we are going to end up with lambda 1 over lambda 2. So we can conclude and say that therefore the refractive index for a wave moving from medium 1 to medium 2 is given by wavelength in medium 1, sorry about that. I said the refractive index for waves moving from medium 1 to medium 2 is going to be wavelength of the wave in medium 1 over wavelength of the wave in medium 2. Exactly. Now, if the incident waves strike the boundary normally, striking normally means that the angle of incidence is 0 degrees. So the incident ray will coincide with the normal. So for this case, there will be no change in the direction and frequency. The rays will not bend, and even the waves will not bend. So there will be no change in direction and there will be no change in frequency, but the speed and the wavelength will reduce, and this happens when waves move from a less dense medium to a denser medium. Please note these 2 points very carefully. We are saying there will be no change in direction and frequency, but the speed and wavelength will definitely reduce. And this is the illustration. Deep water is a less dense medium. You see how spaced they are? Then in shallow water, they are closer to each other, and this is the boundary between the two. Now, if you look at this ray, if you draw a ray perpendicular to the wavefronts, this ray just came and did not change in direction. So there is no change in the direction of the wave, and there is no change in the frequency, but there is a change in the speed and the wavelength. Case 2. Refraction of waves moving from shallow water to deep water. Now what happens the other way around? If you decide to say, let the waves start from shallow water to deep water, and we see what happens. So still remember these points. The deep water is the less dense medium and the shallow water is the denser medium. So thus, the rays, if you consider one ray. So we are saying, thus, if you look at any ray, for that case, it will bend away from the normal. I don't know whether you're relating these things, so they are just confusing you. If they are confusing you, you replay the video so that you understand them well. So the rays thus bend away from the normal. Now the speed and the wavelength of the wave will increase, but the frequency won't change. The frequency won't change. A question. Oh, I was looking for this thing here where I can give you a question and I also relax. So complete the diagram below to show how the waves are refracted. It's supposed to be to show the refracted wave. Oh, the thing also. Complete the diagram below to show the refracted. How did you come here? I've crossed you. Complete the diagram below to show the refracted waves. So we have shallow water, we have a boundary, we have deep water. You complete this one. Let's go to something else. This diagram, you're going to draw it. Someone is scared. I don't know why you fear completing these things. So surprise, I'm going to something else. Yeah, let me even close this curtain. Yes, it's gone. Oh, we have an answer. It's a surprise. So we have a boundary between shallow water and deep water. And we have our waves incident on that boundary. You can see that. So what we're going to do is, you draw a ray. The ray is always perpendicular to the incident wave fronts. And at the point of incidence here, at the point of incidence right here, you see this point of incidence? Okay. So at the point of incidence, you draw a normal. So you draw a normal. You see? You draw a normal at the point of incidence. Now, having drawn the normal, remember, the shallow water, what did we say about it? Is it the denser medium or the less dense medium? Is it the denser medium or the less dense medium? By the way, remember for refraction, if this ray came like this and struck the boundary here, now you cannot put the refracted ray on the same side of the normal. Because the normal is here, this refracted ray always has to cross the normal. But we ask ourselves, is it bending towards the normal or is bending away from the normal? Remember the original direction is here, horizontally. So is it bending towards the normal upwards or away from the normal? That's the original direction. Where does the refracted ray go? If a wave is moving from shallow water to deep water, shallow water is a denser medium, deep water is a less dense medium. It's going to bend away from the normal. I knew you would get it. So it bends away from the normal, just like that. So if it bends away from the normal, so we are going to start from this point here, the point of incidence, and we draw the refracted wave fronts, but we draw them always in such a way that they are perpendicular to the refracted wave. So look at the first one. You see there? This wave front is perpendicular to this one here, to this one. Okay. Then another one, another one, another one, another one, another one, another one. Yes. Wow. Now the thing looks very interesting. What has happened? What has happened to the wavelength? Here it was smaller. What about here? It's bigger. So the wavelength has increased. What has happened to the speed? Remember, the frequency is constant. If the wavelength increases, it means that even the speed increases. Yes. So these are the incident wave fronts here, and then the refracted wave fronts. You can always pause and finish the diagram. So this is what I was illustrating. Yeah, just to take away the things that were probably confusing you. But always when we ask you, you draw this. Hey, you draw this one. Okay. We've already seen that. So case 3, refraction of straight waves at curved surfaces. Now if you have curved surfaces, what happens? The first case, the first scenario is if you're having a converging or a convex refractor. Sometimes they call it a convex lens. Please note it properly. Look at what happens. I have incident wavefronts. They are straight. You saw how they were moving. They were going from left to right. And then along the way they meet a converging, or what we call a convex lens or convex refractor. What will happen? To find out what happens, it's always easier. You consider rays. Now, let's take a ray. If the rays are always drawn perpendicular to the wavefronts, I hope you know that very well. Don't forget. So this ray came, and at this point here, it's bent towards the normal, and further from, not towards the normal. I shouldn't disturb someone, but definitely if you are to follow closer here, it will bend towards the normal. Yes, if you draw normal here, and then even here it bends closer towards the middle point anyway for the lens. If you have done light, this should be very easy for you to understand. So let's take another ray downwards. It will also do the same thing. Now what we are going to do is, in the middle here, within the refractor here, we are going to do, remember the refractor is a denser medium. Therefore inside there, the waves have to be closer to each other with the wavefronts. But outside, they have to be as equally spaced as they were before the refraction. So let's look at what happens. Inside, you see, from here to here is smaller than from here up to here. You can see that difference. Okay. Then, because you see, these ones were converging downwards, that means they would be like that. Then, outside, so you see, these, we shall have circular wavefronts, but they will converge to a point. This point here is called the principal focus of this lens. And then they diverge outwards like that. That's what happens for a converging or the convex refractor. Part B, what about a concave or diverging refractor or diverging lens? Still, let's look at the same scenario where we are going to have incident wavefronts which are straight, and then they meet a concave lens or a diverging refractor or diverging lens. The principle is the same. Take two rays. One ray comes and then it's refracted that way. Then another one also, same story, it's refracted that way. Now when you produce this ray here backwards, and even this one backwards, you realize that since these two rays were diverging, it means they could not meet beyond it. They couldn't meet out there. So the only point of meeting is a virtual point which you just produce backwards. Produced by producing those refracted rays, the emergent rays backwards actually. So remember the technology. Within the more dense medium or the denser medium, the wavefronts have to be closer to each other, and then outside they have to be as equally spaced as they were before the refraction. Okay. So we have here, I've just represented only two. Now remember, this appears to be the virtual source of the refracted wavefronts. So, and that's how they are going to be. That's how they are going to be. The wavefronts after refraction by a concave lens. That's what you end up with. Case 4, if you have straight waves being refracted by a prism. So what happens here? This case is very easy. Straight wavefronts incident onto a prism. What happens? The principle is simple. Always just to draw a ray perpendicular to these rays, and then ask yourself what will happen to bend downwards and further downwards like that. So have represented. A ray came like this, got refracted, got refracted. Let's draw here. We're going to draw here lines, the wavefronts perpendicular to this. We're going to draw in this space lines or wavefronts perpendicular to this ray, and also outside we draw lines perpendicular to this line. So that's what we end up with. Just like that. You can draw this thing properly. Don't say, hey, it looks complicated. No, you can do it. On the other hand, if the angle of incidence was a little different, so that the wavefronts came like this is what we're going to end up with. I am not going to explain this one. You just pause and you do it. Okay. Wow, that has been a short video, but I hope you've liked it. So like and share this video, subscribe to my channel please. God bless you all. And if you have been blessed, please donate to the free science tutorials project. Send mobile money to 0775374719 and it's registered in my name, the host. If you find like I'm asking for money and we just want money and you don't want to support it, please feel free. But I always encourage you that it's good always to appreciate, because we sacrifice a lot to make sure that you learn. And even if you don't have money, I pray God blesses you still. I know you are struggling also to learn. Yeah, let's meet in video part 4, waves part 4. I wish you the best of the rest of the day. God bless you. Bye-bye.